Let's talk about the idea of using something called a confidence interval. First, we'll have to review some things. Again, remember the whole point of studying statistics, the reason that we have statistics, is statistics are a summary from a sample. So when you cannot talk to everyone that you would like to say something about, but you can talk to a few people, then you can produce something called a statistic, which is a measure of the sample, like sample average, sample proportion, or sample standard deviation. And then if we've taken our sample in a way that it actually reflects the population, then we can use our statistic to estimate something called the parameter. This is the population average or the population proportion or the population standard deviation. Okay, so statistics estimate parameters. Okay, so that's the idea. For numeric data, that's data that has number meaning. You can add things up and divide, giving us, of course, the average. And if you have categoric data, this is data that can't be added, then the best we can do is talk about proportions here. So we saw somebody liked the color blue, 7 people out of 10 liked the color blue. So instead of adding up blue plus green plus red, which makes no sense, we simply say there was 7 in the population or in the sample of 10. So 7 out of 10 would be a proportion. Okay, so these are what are called point estimates. They are our best guess. Okay, if we only get one guess, that's what we think. Is going to happen. Is just x bar. That's our best guess for mu. P hat. That's our best guess for p. S. That's our best guess for sigma. However, if you're allowed instead of giving a point estimate, which is just one value, if instead you can say, I believe that mu is in between two values, a range, then you're talking about an interval. Okay, and we can add how confident we are in an interval. Okay, so here, the idea comes from the empirical rule. As we studied, if you're within one standard deviation of the mean or the middle, then you can say you are 68% of the data should fall there, and therefore you can say I am 68% sure that if I say the truth is in this range, that I can be 68% sure of that. If you look at the give or take 2 standard deviations, we saw that the amount of data that should fall in that range is 95%. So here we can say we are 95% sure that P will fall into this range. And if you want to go 3 standard deviations, you can say I'm 99.7% sure that that the truth will be in between 3 standard deviations of my guess. Okay, so that's the idea. Now there are a few things that we need to know. Here, of course, we need the distribution to be bell-shaped, which means we're using the central limit theorem. For proportions, we saw that there are a few restrictions. We need to have at least 10 successes. We need to have at least 10 failures. That's just so that we can have a sample size that's large enough to make sure that the sampling distribution shape is approximately bell-shaped, seeing as we are using the empirical rule, the idea of that. The other thing that you might ask yourself is when you look at here, I'm saying I could choose to be 68% confident or 95% confident or 99.7% confident. Then the question might be raised, well, why not be 100% confident? Okay, and there's a good reason for that. So imagine that you're trying to estimate how you're going to do on your final exam. I can give you an interval that I'm 100% confident is true. You will get in between 0 and 100%. The problem with 100% confidence is that you get an interval that's not very meaningful. The range of your interval is so large, you're not really truly saying anything useful. On the other hand, I can also say I believe that you're going to get in between a 73.7 and a 73.9. Very, very small interval, and I would have very small confidence in that. I'd say, well, I'm about 0.5% sure you'll get into between 73.5 and 73.7. Okay, again, either way, super high confidence and super low confidence might not be actually useful for saying any sort of statement that's useful. Okay, so how do we find these intervals? Now we'll get into the formulas a little bit. Okay, so here we're going to start with our point estimate, and we're going to add and subtract something called the margin of error. Okay, so here I'm saying, well, my best guess is p hat, give or take some amount. That amount is called the margin of error. How this is calculated, it's not unlike Chevyshev's, where we had here, this is what we expect. Here we've got some sort of standardized jump, and then we've seen above from the empirical rule, depending on how confident we want to be, we need to make certain amount of jumps. So let me just go up here and see. If I want to make one jump away, then I'll be 68% confident. If I want to make two standardized jumps away, then I'll be 95% confident, and so forth. Okay, so here Z is the amount of standardized jumps. Okay, and you can see from this formula that the margin of error then is the number of standardized jumps away. So it's this Z times by the standard error. Okay, so when you multiply those two things together, you get something called the margin of error. Okay, so what is the standard error? Okay, so we saw this earlier when we were studying the central limit theorem. Okay, for proportions, the denominator, or the standard deviation of the sampling distribution, was p times 1 minus p divided by n, and take the square root of it. Okay, so that is the standard error, also the standard deviation of the sampling distribution. The unfortunate thing is the whole goal in this confidence interval is to actually estimate what p is. Okay, we're trying to estimate p. So therefore, we don't have p to be able to use in this formula. When we don't know p, what do? Okay, when we have no idea what p is, we estimate it using p hat. Okay, so that's what we're going to do here. Okay, so instead of using p's, we are going to use an estimate, and we're going to say p hat times 1 minus p hat over n, and we'll take the square root of it. So we finally arrive at the formula here. So this is p hat plus or minus some number of standardized deviations, depending on how confident you want to be, multiplied by this thing called the standard error. So this thing under the square root is called the standard error. The standard error multiplied by the standardized jumps is called the margin of error. Okay, so here we can talk about it visually. We want to be 1 minus alpha percent confident. Okay, so in the middle here, we want to have however confident we want to be. 1 minus alpha minus 1 is just alpha, which is the error. Okay, so for example, if you wanted to be 95% confident, then you have 5% error. The 5% will be tucked symmetrically into the greater than side and the less than side. Okay, so this, because we're splitting up alpha into 2, we have here the area on each tail is alpha over 2. Okay, so if we want to be 95% confident, then we must have 2.5% error on this side, on the left side, and 2.5 error on the right side. Okay, we've seen already from studying the normal distribution how if we had an area here, say for example 2.5%, then we could find the corresponding Z value here. So here, let me just do a quick example. Let's say that alpha was 95%. Or sorry, that confidence was 95%. That would mean 1 minus alpha is 0.95. Therefore, alpha is 0.05. That is the error, is 5%. Then here in each tail, there is 5% divided by 2, which is 0.025 area. So how do we find this standardized value? You can use your table. What we're going to do here is look in the middle. This is where the areas are for the value 0.025. Okay, so it's kind of hard to tell where it is, but we'll just keep on scanning and scanning. Oh, here it is right here. 0.025. It is in the row of negative 1.9 and in the column of 0.06. So this value here would be negative 1.96. Therefore, this value here must just be the positive counterpart. That is 1.96. Okay, so then we can build our estimates. This is in the Z scale. We can change it to be talking about proportions by saying this is the sampling proportion, subtract here this value that we found, 1.96, times by the standard error. That is the lower limit for our interval, and the upper limit is p at plus 1.96. 6 standard deviations times by the standard error. Okay, the other thing I wanted to show you is in Minitab, we can do that as well instead of using the Z table. You can go to Calc Probability Distributions. We're talking about normal. It was a Z value. Because it's a Z value, the mean is 0, the spread is 1, and I'm looking for the inverse area. And here I said that I was looking for 0.025. So just like using the Z table, you can use Minitab. You can see here a little bit more digits. This is negative 1.95999. Okay, so here the table has rounded it to 1.96, and we've got 1.95999. Okay, so how do you interpret a confidence interval? Okay, so here let's say that we did a confidence interval and our confidence interval said that we were 95% sure, so I used 2 standard deviations or 1.96 standard deviations if you want to be a little bit more precise. The empirical rule is, after all, just an estimate. So we're 95% sure that P, this is not P hat, we're sure that the parameter P is between 0.42 or 42% and 0.48 or 48%. Okay, so here then, when somebody asks you, is P 50%? Well, here is 50%, 0.5. It is not inside of my interval, so it does not look like P is 50% because it's not inside my guess. My guess was that P was in between 42 and 48, and you're asking me, is 50 P? And I say, I don't know, but I'm 95% sure it's not because it's not in my interval. In fact, I could say something, not just that P is not 50%, but I could say I believe P is actually smaller than 50%. As you can see here, my whole interval is lower than this 0.5. So it looks like P is actually less than 0.5. Okay, so some things you want to be aware of is you don't want to say there's a 95% chance. Okay, so that's not the correct interpretation. Instead, you want to say that you are 95% confident or 95% sure of P, because P is whatever it is. We are just trying to estimate it. P either is 0.5 or is not 0.5. I don't know. It's not that there is probability that P could be 0.5. It is what it is. What we're actually stating is how sure we are in our interval, not necessarily the probability of P. Okay, so that's great. Let me do an example in the next video.